In the last video, we looked at 3 planes intersecting. That was 3 by 3 equations. Now we're going to look at 2 lines intersecting. Now this is actually easier when we talk about 2D because it's just a 2 by 2 equation. But when we get to 3D lines intersecting, some very funky stuff happens. Now let's just review what happens in 2D. So we've got this situation here. If you want, you absolutely can do it on equation solver. So you would go into simultaneous, 2 unknowns, 4, 6, 8, 5, 4, 17. Solve that, and you can see that it's 0.5 minus 2. Just as a little recap, I will show you how to do this with row operations. So it feels a bit weird doing row operations in 2D, or like 2 equations, but you absolutely can still. 5, 4, 17. So we'd want, when we dealt with 3D, we wanted zeros all in the bottom right corner. But when we deal with just 2 equations, we just want a 0 there, basically. That's all we need to do. So the best operation to do here would be that row 2 goes to 4 lots of row 2, take 5 lots of row 1. So that first term there would essentially become 20 take 20, which gives you 0. You then got 16 take 30, so that's minus 14 there. And then when this gets really messy, I kind of just like to go to the calculator. So just to make sure we did that one before right, it would be 4 by 4 take 5 by 6, which does give us minus 14. Then it's 4 by 17 take 5 times 8, so that's 28 just there, and the top row stays exactly the same. So that's done, actually. You can then read off the bottom equation. So from equation 2, minus 14, y is 28. So y is 28 over minus 14, which is a very fancy way of writing minus 2. Which is wonderful news because y was minus 2. You absolutely could use like elimination or something if you prefer to solve it like that, but the point is row operations do work with 2 by 2 equations. Okay, now that we know y is minus 2, you've got 4x plus 6 lots of minus 2 is 8. So 4x take 12 is 8. So 4x is 20, so x is 5. Done. So what we've got here is we've got 2 lines and they meet in a point. And that point is 5 minus 2. Okay, let's look at what else can happen. Same thing with planes. You'll notice that the bottom line is a multiple. Well, it's timesing by 4, it's timesing by 4, and this one is timesing by 5. So same sort of thing with planes. The lines are going to be parallel because the equations are sort of wanting to be multiples of each other. If that was timesing by 4, then the 2 lines would be sitting on top of each other. But since it's not timesing by 4, these lines are going to be parallel to each other. So I'm expecting the answer to be no solution. Let's see what happens. So if we put it into our augmented matrix, I got 1, 3, 5, and I got 4, 12, 25. So you're going to do row 2 goes to row 2, take 4, row 1. So 0, 0, and then 5. So yeah, you get this equation 0x plus 0y equals 5 is that equation from the bottom. And so 0 equals 5, which is a contradiction, therefore no solution. Similar to what we saw in 3 planes. All right, find where these 2 lines intersect. This is literally the same equation. It's just the equations are now multiples of each other. So what I'm expecting is that the 2 lines are coincident, which will mean infinitely many solutions. Let's see how that happens. 1, 3, and 5. You've got 4, 12, and 20. Now let's do our row ops. So row 2 goes to row 2, take 4 lots of row 1. 1, 3, 5 stays the same. On the bottom you got 0, 0, 0. So we can follow the same process we used for 3 planes. So when we dealt with 3 planes here, we threw out the bottom row of zeros because that's an equation which says 0 equals 0, which isn't very useful. I'm going to say let y equal t. And so equation 1 becomes x plus 3y equals 5. So x plus 3t equals 5. So x is 5 take 3t. So this is going to be a little bit weird. The 2 lines meet in a line. The line is x is 5 take 3t, and y is t. This is very silly doing it like this, but essentially the line we've just described there is that line where they're coincident. There's infinitely many solutions. Cool, so those are the three things that can happen in 2D. The same three things can happen in 3 dimensions, but there's one more. So I've made a little fancy flowchart here for 3D lines. Now, the 3 original cases are just here. So they're coincident, they're parallel but not coincident, or they intersect at a point. In 3D, there's one more thing that can happen. It's called skew. It's very hard to draw on a page, but basically the lines, like, they go past each other in 3D. So there's sort of no intersection there, but they sort of like just go past each other and use that 3D space to not hit each other. You can imagine if you drew any 2 random lines in 3D, most likely they would just be skew. Like, they wouldn't meet each other. The chance that 2 lines in 3D actually touch is pretty low because lines are very skinny. Okay, so let's go through this. We'll use our little flowchart to help. Okay, so on our flowchart, and I might just nab a copy of this so that we don't have to keep scrolling back up to it. But the very first thing we want to do is check whether the 2 lines are parallel. Now, how do we check whether 2 lines are parallel? We essentially just look at their direction vectors. So we look at the direction vector B1 for line 1. Now that's just all your coefficients of t. So it's a 1, minus 4, 3. And we look at B2, minus 2, 8, minus 6. So are these multiples? Yes. B2 is minus 2 lots of B1. You can sort of imagine that you would just be timesing by minus 2. They're there and there. Okay, now, so we're up to the yes option here. Yes, the lines are parallel. Now, find any point on line 1. Does this point lie on line 2? So let's just pick a random point on line 1. I'm going to pick the point where t equals 0 because that's often the easiest one to pick. So when t equals 0, I get x is 3. 3 plus 0. I get y is 2. 2 takes 0. And I get z is 0. So we get 3, 2, 0. Now, the question that we ask ourselves is 3, 2, 0 on line 2? That's the question. So line 2, we've got x is 7 take 2s, y is minus 14 plus 8s, and z is minus 6s. So if we want 3, 2, 0 to be on the line, I would need here, s is a half to make, no, I lied, 3. So s is 2 to make that happen, because you would get 7 take 4, which is 3. Here, minus 14, well, let's just try s equals 2 and see if it works, because s has to be the same value for this to work. Minus 14 plus 16 does give us 2, so yes, that does give us 2. So yeah, x is 3, y is 2, that's good news. Alright, next we just need to check the z, so if it is supposed to work, s should be 2 for every bit, so we just check, does s equal 2 work? If we do this, z equals minus 12. Nope, it doesn't work, so no. You can get 3, 2 to work, but you can't get the 0 bit to work. So no, you can't find the point 3, 2, 0 on line 2. So therefore, L1 is parallel to L2, no intersection. So basically, if that third point did work, the 2 lines would be sitting right on top of each other. We'd have infinitely many intersections. But because we couldn't find this point on line 2, we got no intersections. All right, we can have a look on GeoGebra as well. So I've graphed that first line there just by entering the equations for it. There it is, entered those. And then with the second line as well, basically I've entered the equations there. I've just used t instead of s because GeoGebra doesn't like using s for whatever reason. Anyway, the 2 lines do come up. You can see they are parallel. They're sort of going in the same direction, but they're not touching. And that point A was on that first line there, 3, 2, 0. All right, next up we got a new example here. So first thing is just check the direction vectors of each line, B1 and B2. So that's 2, minus 3, and 5. And then B2 is going to be 6, minus 9, and 15. Are they multiples of each other? So yes, they are. B2 is parallel to B1 as B2 is 3 lots of B1. They are straight up multiples. 3 times B1 gives you B2. So on the flowchart, we are now up to this point. We've got to find any point on the first line. Does it lie on the second line? So on L1, the easiest point to pick is usually just t equals 0. So we've got this point 3, 2, 1. And the question is, does that lie on L2? So on L2, the equation is x minus 3 plus 6s. Y is 11 take 9s, and z is minus 14 plus 15s. Okay, so we need to figure out what the s value is. So here s equals 1 would make this equation work, because you get minus 3 plus 6 does give you 3. Let's try s equals 1 and see if we can get 2 and 1 there. So 11 take 9, so y would be 2. So yes, we do get 2. And we get minus 14 plus 15s, so you would get z equals 1. So yes. So therefore, 3, 2, 1, we can say is in line 2. It does lie on line 2. So therefore, L1 and L2 are coincident. So we have infinitely many solutions. If we graph these on GeoGebra, they're the same line. So I can turn F on and you can see it's that line there. I can turn G on and it's the same line. So they're sitting right on top of each other, infinitely many solutions. All right, another pair. Basically, we've explored what does this one look like and what does this one look like. We'll have a look at what the other two look like now. So we'll follow the process. We check the direction vectors of both lines. We see whether they're parallel. 1, 2, 0 would be the first direction vector. 2, minus 5, 3. These lines are definitely not parallel. They are not parallel because they would have to be multiples of each other. You try it, times by 2. Here you would have to times by minus 2.5. So those are different numbers, not parallel. Okay, the next thing we do is we actually set the x's, y's, and z's to each other. So this is why you need to use different letters, t and s, because so 7 plus 2s. So this is the x's are equal. We're going to have another equation for y's are equal and the z's are equal. So we're going to get 2 plus 2t, that's the y bit, equals 1 take 5s. And then we have z equals 4, which is 7 plus 3s. So rather than writing it like that, there's just going to be the equation from the x's, from the y's, and from the z's. Okay, we need to do some rearrangement. So basically, if we put everything in alphabetical, well, not quite alphabetical order, but I'm going to put the t's first, then the s's, then the constants. So this equation will become t. I'm going to bring the 2s over to the left here, take 2s. And I'm going to bring the constants all over to the right. So in particular, that 3 is going to come and subtract from the 7. Equals 4. Okay, from the y equation, we can do a similar thing. So I'm going to have 2t plus 5s equals, and then the constants have to come across, minus 1. And then over here, we're going to have, well, there's no t's, so we're just going to be left with minus 3s equals, and then it's going to be 3. There's 7 take 4. Okay, this is a set of 3 simultaneous equations. It's actually only got 2 unknowns though, so this is a bit different to how we normally solve simultaneous equations. You've got to pick any pair of 2 and just check, try to solve those for t and s and throw out a third one. You pick the two that look the easiest. So I'm going to pick that and that one. Now, this doesn't always happen. Sometimes you have to use like elimination or whatever. But the equation 3 is actually really nice because we just get s is minus 1 from it. And then we can sub that back into equation 1. T take 2s is 4. So t take 2 lots of minus 1 is 4. So t plus 2 is 4. So t is 2. So that's what we get there. S is minus 1 and t is 2. So now that we know that t is 2 and s is minus 1, we can work out the corresponding points for each of those on each line. So just remembering that x was 3 plus t for the first line, y is 2 plus 2t, and z is 4. And then over here, 7 plus 2s, it's 1 take 5s, and then it's 7 plus 3s. So we're about to sub in our t and s values, and if we get the same point, that means we have an intersection. So let's see. 3 plus 2 is 5, 2 plus 4 is 6, and 4 is 4, last time I checked. Over here, s is minus 1, 7 take 2 is 5, 1 take 5 lots of minus 1 gives me 6, and 7 plus 3 lots of minus 1 is 4. Now, because we used the equations for z and x, I already knew that these outside ones were going to match. The x's and the z's should have matched each other. And if they don't, that's a really good way to know that you've done something wrong. The 6 may or may not have matched, and in this case, it did match. So therefore, L1 and L2 intersect at a point, and that point is 5, 6, 4. All right, so there's our two lines graphed on GeoGebra. I just had to use t instead of s for that second one. And if I graph the point 5, 6, 4, oh my goodness, that's where the two lines intersect. Wonderful stuff. All right, there are 4 things that can happen. Here's the 4th. Skew lines. Well, I'm spoiling it there, but they will be skew. Okay, so B1, we got to check whether the lines are parallel first. So -1, 2, -3. For B2, we've got 2, -1, 1. So B1 is, so basically the lines are not parallel. So now what we need to do is take the x's, y's, and z's and set them to each other. So we're going to have 2 take t equals 3 plus 2s. We're going to have 2 plus 2t is 1 take s. And we're going to have 4 take 3t is 7 plus s. We do a little rearrangement on that. So t's first, then s's, then constants. So we're going to have minus t on the left-hand side, take 2s, because the 2s had to move over to the left-hand side. And then when we move the 2 over here, we're going to get 3 take 2. So we get 1 on the right-hand side. Over here, we've got 2t, we've got plus s, and then we've got -1. Then over here, we've got minus 3t. Take s is 3. Okay, so we'll call this equation 1, equation 2, and equation 3. Now, I can see a pair that's going to be really easy to solve. So we'll just look at equation 2 plus equation 3. So basically, I'm just going to be adding these two together. What do we get? We get minus t plus nothing. So that's elimination. The s's went away. And then equals 2. So minus t equals 2. So t is -2. Wonderful. Now that we know what t is, we can just reverse engineer this equation to figure out what s is. Maybe I'll go from equation 2. 2t plus s is minus 1. So 2 lots of minus 2 plus s is minus 1. So minus 4 plus s is minus 1. So s is 3. Okay, now what we need to do is we need to take t is minus 2, s is 3, and we'll plug them into each equation and see what points we get. So I already know that because I used equation 2 and equation 3, I'm really hoping that the y's and the z's match each other automatically. If they don't, you have done something wrong. What we're really checking for is whether the x's are going to match each other. By the way, you absolutely can check in advance. Like if you plug your t and s value into this equation and it works, then you know you would have an intersection point. But I always do this point checking method because if you find that the lines are intersecting, you're going to have to find this point anyway. Okay, so to work out the x value, that's 2 take t. The y value is 2 plus 2t. And the z value is 4 take 3t. And that's just coming from the equation up the top there. So let's see what we get. 2 take minus 2 is 4. 2 take 4 is minus 2. 4 take 3 lots of t. So that becomes 4 plus 6, which is 10. Now let's do our s values. So you've got 3 plus 2s would give us the x coordinate. For the y coordinate, 1 take s. And for the z coordinate, 7 plus s. So I'm really hoping that the y's and z's match and the x's may not. So 3 plus 2s. So that's 3 plus 2 lots of 3 gives me 9. That's fine because they may or may not have matched. 1 take s. So 1 take 3 is minus 2. And then 7 plus s is 10. So thank goodness that the minus 2 and the 10 match. So that's all good. And that means that we have done everything right. But the point that matches the equation that we didn't use for the x values, that bit of the point didn't match. So what it means when that happens, the lines are skew. No intersection. Now let's have a look at what that looks like. All right, so we've graphed the two lines on GeoGebra, and you're probably thinking like, hold on, it does look like they intersect. And that's until you look around in 3D and, oh, no, they don't. So they sort of just go past each other in 3D. They'll never meet. They sort of just fly right past each other. And to be honest, if you wrote down two random lines in 3D, more often than not, this would happen because the chances that these two really skinny lines meet each other is very low. And those are the 4 things that can happen. And hopefully that flowchart is helpful because it's quite the process.